Let's talk projectiles. So I posted a video showing what happens when a bowling ball and a feather are dropped in a silo where there's air in the silo. And we know that the bowling ball, we already knew before it actually happened, the bowling ball will hit the ground before the feather. But then in that video, they took all the air out of the room, all the air out of the silo. And so there was no air in the room. And they dropped the bowling ball and the feather again. And in that time, in that situation, the bowling ball and the feather hit the ground at the same time. That was pretty cool. So my question is, why is that? Well, clearly it has to do with air resistance. And air resistance is causing the feather to not fall as fast as the bowling ball. All right, so we know the answer. But what is really good to do is to take a step back and do a kinetic analysis of the situation, put down some equations, and then make sure we can explain what we already know using the equations. And that way, we actually are making sure we're applying the equations correctly. And we're also checking and making sure we're understanding the situation correctly. Okay, so let's do a kinetic analysis of projectiles. I'll just start with the bowling ball. I'm going to draw it nice and big so we can draw some things on it. But we also have the feather. All right, that's not bad feather. Yeah. What forces are acting on this object? In the kinetic analysis, we identify forces acting on the object. Okay, this is key. We have gravity, and we have drag force. Now notice right now, I drew these the same length, representing that they're the same magnitude. All right, we're going to actually see that that's not always the case. Same thing over here, we've got gravity, which is gravity is pulling on the feather a lot less. Why? Because the feather has less mass, and the feather weighs less than the bowling ball. And then we also have drag force here. It's a different magnitude of drag force that we're going to be looking at, but it's still there. I just drew that as an up arrow. All right, so we know in a kinetic analysis, we identify forces acting on the object, and then we put those forces into this equation, F equals ma. Forces acting on the object equals m, the product of mass of the object times acceleration due to the center mass, or of the center mass. All right, that's our equation. Now what we do is pick a direction, and then we put those forces into this equation. Now, the direction we're interested in right now is vertical direction, not dealing with horizontal motion at all. We're just dropping the ball and watching it fall vertically. So I'm going to put these two forces into this equation. I'm going to have drag force, which is positive. I'm always going to use up as positive, almost always. Every now and then I'll switch it. Plus Fg, which is negative, the force due to gravity pulling down on the object. And you see, these are this equation is for both these situations. All right. Now, an interesting thing, which is good to introduce, is let me go back. Let me draw another situation here of what's really happening. Because again, I drew this force arrow like that. All right, this is one moment in time with this object falling through the arrow. Let's just take a step back and think about what really is happening. I'm going to put the bowling ball here again. All right, and initially when it's dropped, velocity is 0 meters per second. How fast is the object going after 1 second? Well, it's accelerating at negative 9.8. If we get lazy and we say there's no air resistance, we know that the velocity would be negative 9.8 meters per second at 1 second. And after 2 seconds, I'll draw a little further down. Whoops, same object, but not very good. V2, it's going to be traveling, it's going to be increasing velocity at a rate of negative 9.8 meters per second every second. So this is at 1 second, this is 2 seconds. So now we're at negative 19.6 meters per second. Again, if we're not dealing with air resistance, which is a fine place to start. Well, let's think about what's happening with the drag force. Remember, drag force, how do we calculate that? That is equal to 1/2 rho CdA V squared. That's the equation for drag force. This is used in any situation where an object's moving through a fluid. In this case, the fluid is air. Well, what are these parameters? 1/2 is a constant. Rho is the density of the fluid. Air has a density of 1.29 kilograms per meter cubed. That's a good number to start with. It will change based on humidity, elevation, altitude. CD is coefficient of drag. This is a parameter, unitless parameter, that's based upon the shape of the object, how well the fluid moves over the object. So it's based on the shape of the object and how smooth or how the surface interacts with the fluid. Notice I caught myself there. It's not always smooth that we're interested in to reduce coefficient of drag. Sometimes we need to do something a little interesting with the surface, but the coefficient of drag is a function of the shape of the object, how well the fluid moves over it, and also the stickiness of the surface in the fluid. So if we look at the side view of an object, this is not the projectile we're dealing with, we look at that classic teardrop shape, because that tells us, that teardrop shape tells us the air, in this case, air or water or any other fluid, moves over the object really nicely. All right? And that's aerodynamic. Right? But there's also how well or how much this air sticks to the surface, and that can influence coefficient of drag as well. All right, let's keep going. The other parameter in here is A. That's the area moving through the fluid. It's the perpendicular area to the flow of the fluid. So if we're watching fluid go this way, we would actually slice the object here, look at it from this perspective, and calculate the area. For a sphere, we can calculate that based upon the area of a circle. All right, we'll do that. And then the last parameter in our equation is V, and this is really important to get correct. This is the velocity of the fluid. And it's important to stipulate it's the fluid, the velocity of the fluid. It's not the velocity of the object. Now, the velocity of the object will match the velocity of the fluid when the fluid is not moving relative to the object. So in the case of our projectile, as long as there's no wind currents, no fans blowing, or anything moving the air while the object is falling through the air, then we're okay. Our velocity of the object will match the velocity of the fluid. But if we have a current, or if we have air being pushed around the object, maybe by a fan or something, well, then the velocity of the fluid is not the same as the velocity of the object. And in this equation, it's the correct way to present this is to say this is the velocity of the fluid. Okay, and then we work off of that to determine the velocity of the object. All right, so that's the drag force. Well, what's happening here? Velocity is 0, negative 9.8, negative 19.6. So this V is increasing as this object's moving through the air. This is a constant, this is a constant, this is a constant, as long as we're dealing with an object that's not changing shape. All of these are constants, so the only thing changing is V, velocity of the fluid moving over the object, because this ball is moving faster, the air is not moving, so the flow of the air is increasing as the object's moving faster. So the drag force is increasing. So up here, I would actually not draw an arrow here, but initially there's just a little bit of drag, and there's a little bit more, and then a little bit more, and then a little bit more, and then more, and it keeps growing, and it's growing exponentially, actually. Oh, I didn't line up my objects very well. That's okay. So this drag force magnitude is increasing as velocity is increasing using this equation. Now what's interesting is at some point, this force vector will be the same as the force vector due to gravity. Remember, gravity is the other force on here, acting on this object. Gravity is a constant, so F sub g. At some point, my drawing is not very good. At some point, the force due to gravity is going to be the same as the force due to drag. When that's the case, we've reached terminal velocity. Yeah, my writing's terrible. I'll put an equal sign in here. What's terminal velocity? Well, at that point, as we continue to fall through, as this object continues to fall through the air, velocity of object is constant. Therefore, acceleration of the center of mass of the object is 0 meters per second squared. Velocity is constant. All right, let's keep this in mind because this is a good concept to know here. So let's go back to our previous page of notes and look at this. Let's now do at terminal velocity. Let's derive the equation to determine how fast the object's going to be going at terminal velocity. Terminal velocity, A is 0, A of the center of mass, okay? Because remember, if we don't have drag force, the center of mass is going to accelerate negative 9.8 meters per second squared. That's because there's no drag force here. The gravity is pulling on the object, and that A ends up being a negative 9.8 meters per second squared. So the force of gravity adjusts on every object so that the acceleration is negative 9.8 meters per second squared. That's really cool. And remember, this negative sign here translates over here, because that's the equality there. That has to be a negative 9.8. Mass is not negative. So that has to be negative 9.8 meters per second squared. All right, so if we don't have drag, boom, this object will travel or accelerate negative 9.8 meters per second squared. And this object, when there is no drag and gravity is the only force acting on the object, will also accelerate negative 9.8 meters per second squared. They'll actually travel at the same rate. Their velocity will increase at the same rate. They'll hit the ground at the same time. But let's look at the situation where we do have drag and why they're not hitting the ground at the same time. So terminal velocity, F drag minus Fg equals 0 newtons. All right, now let's keep going. Get a piece of paper. Let me put my notes on here. Which one did I start with? I started with this as 1. I gotta keep them straight so I can scan them afterwards. 2, and then now this is notes, page 3. Okay, so now we've got this equation, F drag minus Fg equals 0 newtons. Sorry, that looks like odd. Let's draw this out a little bit more. F drag equals the weight of the object. It equals the force of gravity pulling on the object. Okay. Now, remember, we want to figure out the terminal velocity. So I'm going to put in the drag equation here. 1/2 rho CdA v squared equals, I'll just leave it as Fg for now, but remember Fg is equal to mass of the object times the acceleration due to the force of gravity. Okay. So that's the weight of the object. And I should do absolute here just so I'm not being too lazy. All right, so now what I want to do is solve for V. Now I'm going to solve for V because the air is static. The ball is moving through the air. And so that way, the velocity of the ball matches the velocity of the fluid moving over the object. It doesn't matter which way we look at it. So now we're going to move all these parameters to the right-hand side of the equation. And I'm going to do v squared equals 2 times fg divided by rho CDA. I got that square, so I'll take the square root of both sides, and I'm left with V equals the square root of 2FG over rho CDA, sorry. Or you may see this in textbooks as well, written this way, 2mg. And I hate this because that should really be absolute value of G to be correct. That's just my little C rho CDA. So you may see that equation in a textbook, which is fine. Either way, all right, CDA, CDA. So now the velocity of the object is equal to this stuff over here. Why this stuff? Because the drag force is equal to the force due to gravity acting on the object at terminal velocity. Prior to that, the drag force is changing at a rate due to the velocity of the object. Okay, so prior to that, prior to terminal velocity, acceleration is actually not zero. So if I go back to this part up here, acceleration will not be zero prior to that, nor will acceleration be negative 9.8 meters per second squared, because if there's no drag force, this is negative 9.8 meters per second squared. If there is a drag force, whatever it is, that's going to change the net force acting on the object, and that acceleration will not be negative 9.8 meters per second squared. Okay. All right, so let's see. I think we're here. And this is our equation for terminal velocity. Now, a lot of times, if you have an exam and you include projectiles on that, you have terminal velocity as a potential question. Students will often say, or when I was learning physics, the question would be, well, can we bring in notes, and can we bring in a cue card of equations? One of my favorite physics prof, Van Dam, back in Buff State, he said, yeah, you can bring in an equation card, but you can only write one equation on that card. And he said that equation just needs to be sum of forces acting on the object equals ma, mass times the acceleration due to the center mass of the object. You can derive almost all your equations off of this, and he was pretty correct for the most part. Sometimes we get off in different directions. This equation looks terrible, but that's just this equation for a situation where these two forces add up to zero. And then we just substitute the drag force equation for F drag, and then we just do our algebra to get V by itself. All right, so super easy actually. So let's look at this again a little differently. Let's look at a spreadsheet I put together for terminal velocity. All right, so now you're looking at a spreadsheet, and let me go through what's in this spreadsheet. Let me zoom in a bit here. So up in this top corner, I just put all the constants. So here's the bowling ball, here's the feather data, here's 1/2 rho CDA, V squared. Here's rho, 1.29, that should be kilogram meters cubed. Oh, I can't get the cube in there quickly, so I'm going to skip that. CD, unitless parameter, is 0.5. I actually had just looked it up. This is the CD for a sphere, and this would be based upon the bowling ball. And so I did Google that. And I also Googled what the CD would be for a feather. Now, obviously, feathers come in all different shapes and sizes, but I had a range to pull from, and I just picked a typical CD4 feather. We don't know what this is for the feather that was used, but it's higher than the bowling ball, meaning the fluid gets disrupted more moving over the feather than over the bowling ball. And then A is the area perpendicular to the flow of the fluid. I just calculate the area of the bowling ball. Oh, that's bowling ball. I can't even spell bowling ball. That's just the area, pi r squared. Okay. I just took a typical size bowling ball. And then for the feather, I estimated how big the feather was in the video, maybe about 2 centimeters wide and 10 centimeters long, something like that. So I took a guess, all right, but that's an area of the feather. And then what I did is I just took the product of those just to make it easy to put in my next equation. All right, so now let's look down here. What do I have? I've got velocity in this column, and I did increments of 5 in here. So 0, 5, 10, 15, 20. These would be meters per second. Then I calculated the drag force. And I calculated the drag force by taking the product of all these elements times velocity squared. I did that in the wrong order, but it doesn't matter. A12 is this cell right here. That's squared times 1/2 rho CdA b squared. So this column represents the drag force acting on the ball based upon these parameters. Then over here, I just put in the weight of the ball. The force due to gravity acting on the ball is a product of mass times 9.8. I put 9.83, it doesn't matter. 70 newtons a ball weighs. So this is a 16-pound ball, roughly. That's a constant. That's not changing. Drag force is here. And I did the same thing for the feather. And for the feather, I used an increment of 0.02. I played around with this a little bit, try to get that graph to look good, and we'll see the graph in a second. So this is just incrementing at 2/100ths of a meter per second. So realize I did 5 meters per second over here, 2/100ths of a meter per second over here. And you'll see why in just a minute. I calculated drag force, same equation, V squared, so D12 squared, times the product of 1/2 rho CdA. And then I put in the weight of the feather here, the force due to gravity acting on the feather. And I had to look this up. And I found that 55,000 feathers would equal a pound. So I used that to calculate the mass of the feather. And this was, obviously we don't know the size of the feather. We don't know exactly what it was, but that's not a lot of mass or a lot of weight. This is newtons here. So this is less than 1 newton, less than 1/2 a newton, less than 1/10 of a newton. This is it doesn't have a lot of mass and therefore it doesn't have a lot of weight. All right, so then I just calculated those or pulled those calculations down to different velocities in this column. So I didn't make a mistake. I just put a quick if-then statement in here, and I wanted to see at what point the drag force would be greater than the weight of the feather. I didn't do it over here because it was easy to pick it out. Right here, right here. The drag force is less than the weight. Here, the drag force is greater than it. I could figure out that velocity exactly, but I just, I did 5 meters per second increment. And here's my quick switch. Here, the drag force is less than the weight of the feather. Here, it's greater than the weight of the feather. So quick, little easy if-then statement. All right, so then up here, what I did is I took that equation we did, that we derived earlier, and I calculated the terminal velocity of the bowling ball based upon these parameters and using that equation that we derived. So 2 times the mass of the ball times the acceleration due to the feather, so that's the weight of the ball, divided by the product of rho CdA. And I took the square root of all that. And I got 76.07 meters per second. That would be, from that equation, the terminal velocity. That'd be the velocity at which the drag force is equivalent to the force due to gravity. All right, 76, how fast is that? Ooh, that's fast. That's over 150 miles per hour, over 160 miles per hour. That's fast, okay? 162-ish miles per hour. I did the same thing for terminal velocity of the feather. Just calculated 2 times the weight of the feather divided by the product of rho CdA, and took the square root of all that. That's just the equation we used, and that's the terminal velocity of the feather, 0.29 meters per second, less than 1 meter per second. So less than a mile per hour. At less than a mile per hour, the drag force would be equal to the weight of the feather. And at that point, it's going to fall at a constant velocity, roughly, you know, yeah, it sways back and forth, but you get the idea. All right. So the terminal velocity of the feather is reached so much sooner than the terminal velocity of the bowling ball. Because remember, the bowling ball is accelerating this entire time up until 76.07 meters per second. Once it reaches that velocity, the drag force is the same as the force due to gravity, and acceleration is 0. So this bowling ball is going to be traveling faster than the feather for that flight, and that's why it hits the ground first. Here's what the data look like in graph. I always like to graph things out. It's a good way to catch mistakes, good way to see things. So what do I have here? I have the bowling ball data. I've got drag force on the, I should just made this force because I do have weight here. So maybe I'm going to just delete that. It'd be more correct to say force because I have the weight of the object right here. That's the weight of the bowling ball. It's constant. And then here I have drag force. So this is the drag force. It's increasing exponentially. It's increasing at velocity squared because 1/2 rho CdA, those are all constants. And V squared is obviously not a constant, it's increasing exponentially. So here, the drag force is increasing, increasing, increasing. The ball is getting faster and faster and faster and faster. And then at this point, it reaches a point that the drag force is the same as the force of gravity pulling down on it at acceleration 0. It's going to be right here. That's so cool. That matches up with the velocity calculation we did. So we're using 2 different ways to get terminal velocity. One, I just used a single equation. And 2, I'm just graphing the data out. And I could actually get a finer, increment of velocity here, and I'll get to that same exact number. Those 2 lines cross right where velocity is 76.07 meters per second. And after that point, this is fictitious data at that point, because really at that point, the drag force would be constant because velocity would be constant. I should fix this in this plot. But those blue circles would not keep increasing. They wouldn't keep increasing if I had a heavier object. All right, but hopefully you get that point, that velocity would be constant, therefore the drag force would be constant, and those blue circles should travel right along the same line, and acceleration would be 0. Here, acceleration is negative 9.8 meters per second squared. Here, it's a little bit less. Here, it's a little bit less. Here, a little bit less. Here, it's something quite less than negative 9.8 meters per second squared. So the ball is not increasing velocity at the same rate here as it is over here. And then here, acceleration is 0. Remember, F equals ma, sum of forces acting on the object equals mass times the acceleration of the center mass of the object. And that's important to always know and always state it that way. All right, that's the bowling ball. Let's look at the feather. That looks about the same. Well, it is the same, except that we've got far different values over here. And again, I better be correct. I'll just say this is force because I've got weight here. That's the weight of the feather. Here's the drag force, increasing exponentially because 1/2 rho CdA, those are constants, and V is squared. So this velocity is increasing, and drag force is increasing at the square of that. So the acceleration of the feather initially is negative 9.8 meters per second squared. So less than that, less than, less than, less than, and eventually it gets to 0. 0 acceleration of the center mass of the feather, because the drag force will be equivalent to the force due to gravity. And those 2 will add up to 0. 0 acceleration, constant velocity. And again, just like before, I should have made these red circles go right to the same value as the green circles. But I messed up. I should have, I was doing this more just to show that crossing of the lines. Oh, and look, it crosses right before 0.30. Ah, how cool. That matches. And that's the same equation that we derived. 2 times the weight of the feather divided by the product of rho CDA, and take the square root of all that. So 2 different ways to get to the same concept. Let me zoom out now. So now you can see these plots look the same, but they're really not, because these magnitudes are so much lower. In fact, I did put them right up here. The gray area right there, that's all these data right here. I can't see it because this is 160 newtons. This is 0.00018 newtons. This is far less than 1 newton, so it's not even showing up on this scale. So my scale is way off here, so that's why I just built 2 plots. And I also only went to 0.4, a little faster than 0.4 meters per second, but here I'm going over 100 meters per second. Again, just to illustrate that we reach that terminal velocity for a bowling ball. So if you take drag force out of the situation, I'll go back to my equation, and then I only have the force of gravity acting on the object, and the acceleration of the center mass will be negative 9.8 meters per second squared, regardless of if it's a feather or a bowling ball. But if I have air and I have drag force, then I have these forces acting on the object, and I have to count for that. Well, the bowling ball has so much more mass that these forces, these aren't big forces. 20 newtons, that's 4 or 5 pounds. This is a 16-pound ball, so this is 16 pounds of force here. It's not a lot, but the drag force is having very little influence on the acceleration of the bowling ball because the bowling ball has so much mass. So if I push on this with whatever this is, 1.2 newtons it looks like, it doesn't really impact the acceleration that much because the mass is so big. But 1.2 newtons applied to a feather, well, I'd be off this chart. I'm way up here, given this scale. And that's really going to influence the acceleration of the object. In fact, that would make the feather go upwards because the force of air pushing on the feather would be greater than the force of gravity. So that would actually propel the feather upward. So the mass of the feather is so small that any little force acting on it is going to have a big impact on the acceleration. Another way to think about this, another exercise I like to do is do throw a golf ball versus throwing a ping pong ball. About the same size object, so the 1/2 rho CDA would be about the same. Very different masses. And if you just think about it, you can throw a golf ball much farther than a ping pong ball. Why? Because the drag force, in terms of the parameters, rho CDA, would all be the same. But the ping pong ball has such a smaller mass compared to the golf ball that any little force acting on the ping pong ball is going to have a big impact on the acceleration of the center mass of the ball. Okay, so that's a lot on projectiles and dealing with drag force and projectiles. Hopefully you picked up something on terminal velocity, and hopefully you can explain why the feather hits the ground at the same time as a bowling ball when there's no drag force, and then why the feather does not hit the ground at the same time as a bowling ball when there is drag force. And the answer is because there's a force of air resistance acting on the feather has an impact on the acceleration of the center mass, and the feather has very little mass, so any little force acting on the feather is going to make that feather reach terminal velocity, constant velocity, earlier than an object with more mass, in case of the bowling ball. More mass, terminal velocity will happen later, which means it's going to be falling faster for a longer period of time and hit the ground first. Okay, I hope that was helpful. Thanks, everybody.